In this video, we look at some of the theoretical considerations and practical experimental variables that we can use to control or affect the rates of chemical reactions. The fundamental underlying differences in rates of reaction for different chemical processes lie in the chemical nature of the reactants themselves. Now, during chemical reactions, bonds are typically broken and new bonds are formed, and it's the inherent tendencies of the atoms, molecules, or ions to undergo bond breaking and bond forming processes that result in different rates of reactions for different chemical reactions. At the molecular level, reaction rates depend on the interaction of reactant molecules or ions, and in particular the nature of the collisions between the reactants, including the frequency of collisions, the orientation of those collisions, and the energy of the collisions. The greater the frequency of collisions and the more that colliding species can be brought together in the correct orientation with sufficient energy to allow bond breaking and bond forming, the greater the rate of reaction will be. So in terms of the frequency of collisions, reaction rates are maximized when we maximize the rate of collisions between reactant particles, and we have a couple of experimental variables that we can control. For example, if we start with a relatively low reactant concentration or a relatively low temperature, we're likely to have relatively low collision rates and therefore relatively low reaction rates. On the other hand, if we start with relatively high reactant concentrations or relatively high temperatures, we are likely to have a relatively high collision rate and therefore relatively high reaction rates. In terms of the orientation of collisions of reactant particles, it turns out that most collisions between reactants are actually ineffective and they don't lead to the formation of products. This is because even if the reactant particles come together with enough energy, they are typically not oriented to allow bond stretching and bond breaking and also formation of new bonds. So for example, let's consider the decomposition reaction of nitrosyl chloride to produce nitric acid and elemental chlorine, and it can be represented via this chemical equation or via the space-filling electron cloud diagrams of the reactants and products involved. If the reactant molecules collide with this orientation, where there is limited opportunity to form the required bonds between the two chlorine atoms, then there is little chance of an effective collision leading to product formation. Similarly, if the reactant molecules collide in this orientation, there is also limited opportunity for the appropriate bond breaking and bond forming. If, however, the reactant molecules collide with this orientation, there is much greater likelihood of the breaking of the nitrogen-chlorine bond and the forming of the chlorine-chlorine bond, and therefore a much greater likelihood of the reaction actually proceeding. The energy of reactant particles and the energy of collisions is also an important consideration. For example, in the electrophilic substitution reaction between bromomethane and the hydroxide ion, the reactant species need to come together not only with the right orientation, but also with the right amount of energy to stretch and ultimately break existing bonds so that new bonds can be formed. The amount of energy needed to allow a reaction to proceed to any significant extent is called the activation energy. So if the energy of the reacting substances is low relative to the activation energy, then the rate of reaction will be slow and the reaction will not proceed to any significant extent. Experimental factors that can be used to control or ensure that there's enough energy to overcome the activation energy include the temperature. The higher the temperature, the greater the energy of a reactant species, and therefore the greater the rate of the chemical reaction. And we can also use a catalyst, which typically acts to lower the activation energy of a chemical reaction and therefore greatly speeds up the rates of chemical reactions at a particular temperature. So there are at least 4 experimentally controllable factors that we can alter to affect the rates of chemical reactions. The first involves the physical nature of the reactants. Now, most chemical reactants involve two or more reactants which must be able to be physically mixed in order for the reaction to proceed. And the more readily reactants physically mix and intermingle, the greater the rate of reaction. It's for this reason that chemical reactions are rarely carried out in purely the solid state. Most of the reactions that we consider are homogeneous reactions that take place in either the liquid or the gaseous state. When reactions take place in different states or even in different phases of the same state, we say that the chemical reaction is a heterogeneous reaction. And in heterogeneous reaction, the chemical reaction is limited to the contact area between the two phases. So, for example, the chemical reaction between reactants dissolved in these two different liquid phases would be limited to the contact area between the two phases. And it would be normal practice to thoroughly shake this reaction mixture in a separating funnel such as this to ensure that we maximize the contact between the two reactant phases and therefore maximize the rate of reaction. Likewise, the heterogeneous reaction between solid iron and oxygen gas in the formation of rust, or Fe2O3. This is a heterogeneous reaction that is limited to the surface of the solid iron. Lack of mixing and limited contact between the oxygen gas and the solid iron atoms below the surface limit the frequency of collisions and therefore limits the overall rate of the reaction of this rust forming process. Another experimental variable that we can control relating to the physical nature of the reactants is the surface area of solids in a heterogeneous reaction. So for example, if we were to physically pulverize an iron sample, its surface area would be considerably increased, thereby increasing collision frequency and thus increasing the overall rate of this rust-producing reaction. Along similar lines, if we had a 5 kilogram piece of wood in the form of a log or a piece of timber, it would take considerably longer to burn than if we were to burn 5 kilograms of sawdust. The increased surface area of the sawdust would allow greater contact between the reactants and therefore an increased rate of reaction. The second general experimental variable that we can readily control is the concentration of reactants, and most chemical reactions, whether homogeneous or heterogeneous, produce or proceed faster if the concentration of one or more reactants is increased. And we deal with the relationship between concentration and rate in subsequent videos in much greater detail, but for now we can consider the difference in the combustion reactions which occur in air and combustion reactions that occur in pure oxygen. Combustion reactions in air, which contain about 21% oxygen, can proceed readily enough at quite rapid rates, but they actually occur much more rapidly and give off much more energy in a shorter period of time if they are carried out in the presence of pure oxygen. In this case, the frequency of collision between reactants is increased by increasing the oxygen concentration, thereby increasing the overall rate of reaction. A third experimental variable that is readily controlled is temperature, and the rates of most chemical reactions increase as we increase the temperature. And this is why we place dairy products in the refrigerator, for example. The biochemical reactions of bacteria that lead to the spoiling of milk occur at a much slower rate at lower temperatures. Increasing the temperature of a reaction mixture increases the energy of the molecules involved, thereby increasing the vibrational, rotational, translational motion of molecules, and this in turn increases the collision frequency and provides more opportunities for molecules to collide at the correct orientation with sufficient energy. Now, a general rule of thumb is that the rate of a chemical reaction will double for every 10 degrees Celsius rise in temperature. The final experimental variable that we can readily control to affect reaction rates is the amount and presence of a catalyst. Now, a catalyst is a substance that increases the rate of a chemical reaction without itself being consumed in the chemical reaction. Catalysts alter the nature of collisions between reactant molecules via a range of mechanisms, but in general, all catalysts tend to lower the activation energy required for a reaction to proceed. This means that for a given set of reactant concentration, a catalyst will increase the rate of reaction without the need to increase temperature. Catalysts play a crucial role in countless industrial processes, including chemical synthesis. They play a critical role in living organisms as well. For example, the enzymes that govern our physiology are catalysts which speed up the rates of crucial reactions in all major biochemical pathways. Now we can use the example of the combustion of glucose in the presence of oxygen to produce carbon dioxide and water as an example. The energy diagram shows that to perform this reaction in the laboratory, we would need to add a lot of energy. For example, by igniting a sample of glucose with a flame just to kickstart the reaction. In other words, we need to overcome the activation energy barrier to set up the right conditions for bond stretching, bond breaking, and ultimately new bond formation. Now, this same overall reaction, the oxidation of glucose to form carbon dioxide and water, occurs in our body when we break down glucose to form carbon dioxide and water during respiration. And through a series of enzyme catalyzed reactions, we can see that the activation energy can be significantly reduced, such that the reaction proceeds well enough and at a good rate at body temperature, much less than what would be required in the laboratory when we burn a sample of glucose via conventional combustion processes.